Hello and welcome to Risc-V manipulation in a high-level language. This is a series of live coding sessions where we develop interesting software around the Risc-V processor architecture. Last session, I struggled with my computer working on the text assembler, and I'm hoping that today my machine will behave a little bit better. So let's just jump straight into this. Um, we um, we were talking about symbols, and I thought it might be a good idea to step back a little bit and see how far we've gotten in our text assembler. We have now successfully tokenized all the tokens that we expect to exist in an assembler file, and we're starting to work on the parsing pieces. And we implemented a few methods to allow us to peek and get tokens. This is the unit test that are for that purpose. But the next thing that we want to do is consider the assembly of the whole file as a whole. So we're going to go back to the assembly language file and then take a look at the method assemble line that we did last time. Well, it turns out that assemble line makes a lot of sense to call it from another method, and we're just going to call it assemble file, like this. And we're going to have it return, let's start with bool. Uh, and the bool flag tells us whether the assembly was successful or not. So we'll return valid when this is completed. And then all we have to do really is just do a loop that loops uh, infinitely reading assembler line, but it needs to stop. So let's change the signature of assembler line so that it also returns a bool, but in this case, bool means continue assembling. So we'll say while assemble line uh, do nothing. So what this will do is it will keep calling assemble line until assemble line returns false. So now we need to change assemble line to do what we wanted to do. So for now, let's just return false. And just to make the compiler a bit quiet, but now we need to think about what should assemble line do. We started here with writing some code, but there's no unit test to guide us. So I'm going to go back to our unit tests and write a little bit of more sensible unit testing code. So now that we have assemble file, we should be able to do this. Um, let's do an empty file. We should be able to handle that. This is a edge case, but it's an important one. So my test assembly is just the empty string, so no contents. And then I create a assembler. Like so. And now that I have an assembler, I am going to call tasm.assemble file. And I expect this to return true because there are no syntax errors because there's no content in the file. So I'll say assert that is equal to or is true. Now if we run this, it's going to fail because we just made the read line function return false, or assemble line return false. Let's see if our unit tests are a little faster today, and it looks like it. Very good. Okay, we're not getting an error that I was expecting, so let's take a look and see. Yeah, we're returning valid because the file is valid. Fantastic. Okay, so that takes care of that, I guess. We do want to handle the case when assemble line. Okay, so let's shift our focus to assemble line. Um, then. So assemble line will assemble this one line, and this is a valid line, but we also are hitting the end of the file. So if we run this, we should get an error this time because that function is always returning false. Interesting. Let's take a look. Uh, I'm not convinced by this unit test, so let's go back to our empty file. And let's run that in the debugger and see what's going on. So here we go. We're starting our debugger. We get a token. Now that token is going to be end of file because there is no content in this file. So there's our end of file. And we're supporting returning false. And this assertion should fail. Oh, there it is. Okay. So this is Visual Studio Code not building my unit test. Okay, fine. All right, so we've now verified that that is indeed happening. So what we do want to have happen here is if we reach, if we read a token, and that token is the end of file, then we want to return false. This means stop assembling uh, because there is no more data to fetch. So we will change that to is false now. But if we have an empty line, and remember we can use carriage return line feed for that, then this is actually two lines. There's the first line, which is empty, followed by the carriage return line feed separator, and then another empty line followed by the end of the file. So we should be able to get the following sequence. If we assemble the first line, we should get true back, and if it is successful, then we'll proceed to the second line, and that should return false. So if we run that unit test now, assuming that all the unit tests succeed, we'll call it 2 lines. Let's run all of our tests again. And now this should fail because we're not handling the case of a empty line specifically. Well, that's interesting. Why is it not finding our unit test? All right, let's run everything again. And then see if we can get the... Huh. All right, let's build the universe. I am struggling with Visual Studio Code these days. It doesn't really behave the way I expect it to do. But we're not going to blame our misfortunes on our tool. So here we go. There's our 2 lines. We're expecting this to fail, and indeed it is, because that first line should have returned true. And that's easy enough to fix. We just need to check for that particular token. If token equals token dot end line, then we return true, indicating that this line was successfully assembled, but there may be more input. Okay, so if either of those two checks fail, then we are expecting words because the first token on any uh, assembly language line is a word. So if it's not a word, then uh, we should probably signal an error. So let's write a test for that. We'll say that the test is, I will call it line not beginning with word. So if the line does not begin with a word, then this is something we don't know how to handle. And so let's put a 3 there, then that should assemble, yeah, we'll tell it. Mm, okay, so if we get garbage in our line, like say we have this, we probably want to do the following. We'll probably want to synchronize until we see a well-known token that is safe, so to speak. A common choice is to find the terminator of a construct, like in this case, a new line. So if we run into garbage, then what we want to do is just skip until the next line. So let's simulate this, or well, let's test this. So we'll run assemble a line, and that will return true because it will eventually hit this. But yeah, let's run this test and see what happens. So this should, I'm not sure what the code will do today. Today it will return false. So what we do want it to return true here because, and let's write a comment to that effect. Returns true if a line was processed by the assembler and more input is expected. Returns false if we have reached end of file. Let's just make that a little clearer. So if we receive a token that is not the expected one, then what we want to do here is say if token is not equal to token word, then what we want to do is write an error like unexpected. And then I guess we'll need to add a new overload, unexpected token, to complain about this token. We need to set our valid to false. What we also want to do is skip until. So we'll return skip until, which is a new method where we are going to be skipping all tokens until we see a token end line. And that will allow us to resynchronize the assembler to a well-known state, which is the end of a line or the beginning of the next line. So let's implement skip until, and let's implement unexpected token. So skip until is a simple while loop. What we're going to do here is loop, and we'll say while get, and here we're just going to discard tokens. While get token is not equal to token.end of file. If it is end of file, then we'll return a false, indicating that there's no more input to consume. But if the token, let's see, we'll have to do it this way. So var token equals get token. If token is equal to end of file, then we'd return false. But if the token is equal to the end of line, then we are returning true. Otherwise, we'll just keep consuming tokens until either one of those two conditions occurs, and we're guaranteed that the end of file will eventually happen. So if we have an error, then we will be able to skip any other tokens. And then unexpected token will be a little message. And then we can say get, and we'll just take token and print it to the user. And also what we could do is move the valid is false into the unexpected token method like that. Good. Right. So let's go back to our unit tests now. So we wanted to test TASM line not beginning with word. Let's clear the filter and run all of our tests in the background. And we expect this now. Well, we'll see what happens. It should assemble a line successfully, but if we then finish the assembler by calling assemble file, this should be false now because we've set the error flag when we encountered that one well, this unexpected token 3. So let's run this again. With a little bit of luck, all our tests will pass. Okay, fantastic. Now, let's go back to, well, we're here. Let's now simulate that we have encountered a label. Um, so if we find a label, what we want to do is verify that we in fact have a new symbol after the label was encountered. So let's write a little piece of, let's copy this. Um, so what we want to do here is confirm that we saw a label. Let's call the label label. Why not? And remember that the colon is the magic entity that tells us that this is actually a symbol definition and not an operand or a mnemonic or a directive to the assembler. So here we are, we're assembling label, and now label will be assembled with, let's just do assemble file. And this should not return an error. And then we also want to confirm that in the assembler, it should have a symbol count of 1. So assert that is equal to 1. So we have one symbol, and we should assert, well, even more concisely, we can say, well, let's just add another, assert that, so that TASM dot symbols contains key label is true. Let's take a look at the other. Oh, we already wrote this test. I had forgotten. Okay, great. So we don't need to write this again. But we do want to test for another condition, which is two labels, same line. This is perfectly valid assembly language. You should be able to say label too. And then we should have a count of 2 labels, and this test should validate that. And I don't think that our code is capable of handling this right now. Indeed, it's not. So it's unhappy because we didn't see the second symbol. And the reason for that is quite simple, is because after we've detected the first symbol, we don't continue looking for more tokens. So what we need to do really is make a while loop out of this. And so what we'll do is we'll make the loop right here. And we will need to export this variable, the word that we eventually see. And then this if statement is no longer necessary really because we've already checked that it's not a word. So if we skip this if statement, then we are a word. So we can successfully read the token string like this. That is good. Like that. But we're now inside of a for loop. And so what we want to do is continue adding symbols. And then we want to leave the loop if we find something that is not a colon. So we'll do this. And then that. Do we like this? So let's take a look at what happens. So we read a token. If it's the end of file, we go. If the end of line, we go. If it's not a word, then we're not expecting this situation. Otherwise, we grab the string, and if it's not followed by a colon, we fall through to here, and this is uncharted territory. But if it is a colon, then we discard it, of course, and then we read the symbol and add it to our symbol table. Okay, so that should do the trick. At the end, yeah, at the end of the line, we have to handle the cases where we actually have some assembler language code. Good. Okay, so that passed. So now let's go back and add another unit test. This time we're going to write assemble an instruction. So we'll assemble add I because that's our most familiar, most common instruction. So here is a little add I. Add I, um, put some, put the number 1 into register 2. As usual, register 0 is a pseudo register that always returns the value 0. So this is the same thing as initializing register 2 with the literal value 1. So how do we test for this, though? Well, the first thing that we need to do um, is to, let's see, we'll want to compare the output that we're doing here with the output that we would have expected if we ran the older assembler, the previously existing assembler. So one thing that we could do is after we assemble the file, first of all, we need to verify that the assembler did the right thing. Also, at some point, the assembled section needs to be returned out of the assembler, and we're not doing that anywhere. We have access to it, but I think a nice way to do this would be to um, instead of making this a property, why don't we make this a return value from assemble file? And what assemble file will do is return the section if the assembly was correct, but if any errors occurred, then there's no point in generating any executable code. So we will return a null in that case. So that looks good. Yes. So some of our unit tests will fail now because they are not testing the right thing, but that's all right. So at the end, when we've done the assembly now, we will have a section. So we'll say var section equals asm.tasm assemble file. And then we'll assert that section is not null. Interesting. So there's no. Okay. Will this work? I have no idea. Okay. So the second thing that we want to do then is create another, what do we call this? Code assembler. And we'll give it a logger. And then what we'll want to do is ask it add I, and we'll pass in 2, 0, 1. And then that assembler also has a section. And so what we'll want to do now is compare those two sections to make sure that they have the same contents. So we'll say assert that section.get assembled bytes is equal to section or chasm section assembled bytes. Good. So there's our unit test. Will it pass? Very likely no. Of course not. I mean, how could it? This test is failing where though? Let's see if we can determine where it died. Yeah. So there's no data in our assembler section. So let's go to our text assembler section or the test assembler here, and we're going to write the simplest possible uh, code to make this pass, with the understanding that we will be continuously refining uh, the code in the future. So here we'll say uh, we have seen a word, classify it. So we'll do this initially. We'll switch on the word and say if the word is add I, then we would love to create, um, in fact, you know what? A good idea would be to use the existing assembler as an implementation detail of this class. That sounds like a great idea. And then we will just use its section. So we can get rid of this property. Well, actually, let's do this. We'll create a member variable called private assembler asm. This is our internal assembler. And we will create this here. And it needs a logger. So let's create an overload for this class where we pass in the logger, a new logger. And this is just to make the unit test pass. We'll make this obsolete so that we remember to remove it in the future. But then this new method then will have a logger. And what we'll do is we'll pass the logger straight on to the assembler like that. Great. And then the section property, we no longer use our own section. We'll just piggyback on the internal assemblers section like that. Okay. What other errors do we have? Okay, so now if we see an add I, what we can do is just call asm.addI. But we first need to process the next two symbols. And so we'll write a method called expect number, because what we do is expect two numbers to follow, or three numbers to follow this token. So we'll expect number, and that will be the destination register. And then we'll have source 1 will also be a number, and source 2 will similarly be a third number. And with those three numbers, we can now call add I, passing in dest source 1 and source 2, and break. And then we need to have a default case here. Here we'll just throw an exception for now, not implemented exception, unknown mnemonic, or directive, and then the directive name, W. There we go. So now we have to implement expect number, which is pretty simple. What we do is we say var token, well, we don't even need hang on. We'll just say if get token is not equal to token.number, then ooh, we will set expected. Oh, we'll just write the error message. Actually, no, we'll have a common case. So expected number, and this will set the valid state to false, and then we'll return 0. Let's write a I will say like that. And then this is just a void function. We're just reporting that we're expected something, but it also sets this dot valid to false. Good. So if we don't see a number, we complain that we expected a number, and then we return a default value. And we also set our valid state to false. Otherwise, if everything did go well, then we have a number. So we return this dot current value. Recall that we build up the current value inside of this property when we're parsing a number. So if everything goes well, then we will get three numbers out. We will put them into the assembler using this instruction, and then at the end, we will uh, we will hopefully have joy. So let's see if this succeeds. I'll be very happy if it does in the second try. And we're getting slow again. I'm not sure what my machine is doing that's causing this, but it is sluggish. Okay. All right. This is failing, right? Because this is no longer true. Let's change this to is not null. Okay. And then here, this also needs to be changed to is not null. So, but add I appears to have worked. That's great news. Okay. So, emboldened by this, we'll add another instruction. Let's add the regular add just for fun. So add looks like this. And in this case, we're adding, this is adding the register 1 contents to the register 0 contents, which are always 0, and putting the sum of those two, which is 0 plus the contents of register 1, into register 2. This is to say, this is a copy. We're copying register 1 into register 2. And this then should match that. Fun. So let's run all of our tests. And we're expecting a failure now because one, uh, that one function has not, or that one instruction has not been implemented yet. Okay, this guy, this one is null. I'm sorry. This one is null because we are failing. We have some errors. Okay, right. So where was the other error? Let's run these again. Expecting two errors. And here's our second error. What happened to it? It's in the assembler tests. Oh, text assembler tests. Here. Indeed, add is unknown. So let's add add. And of course, this is going to be very similar to the one we already did, which is this. And so we'll do something very similar. We might as well copy this whole thing, and then we can reuse these variables. And then this is now add instead of add I. And if we run all of our tests, then this should pass again. Fantastic. So at this point, we could spend a lot of time, a lot of your time, uh, looking at or implementing most of these instructions. But as you can see, it's a fairly mechanical process. However, there are some possibilities for improving the code. You'll notice that we are repeating ourselves a lot. The sub instruction, for instance, would look exactly the same. We might as well toss it in there since I just mentioned it. We'll just do this and then do that, like so. And this is rather tedious. There's a lot of code being written here. And when you see code getting repeated like this, that is usually a sign that there's a way to make this more compact, more efficient. And my thinking here is that if I recognize add, then I want to do something very similar to what asm.add does, which is um, look up this information from a table someplace. Um, so if I were to steal this binary encoding, and let's suppose that I had in here a table. I'm going to call it a table of ASM encodings, or ASM encoders. And it would look something like this. We'd have a new ASM encoder, and the ASM encoder would contain the symbol, so ASM or add in this case, and then maybe an opcode, which is this thing here. And then maybe we could have a pointer to a function or a method that is responsible for encoding this into the appropriate instruction. So the handler for this. So let's write a method called um, asmr. Why not? Okay, so asmr would be a method on this class, and I need to make it a static method. So reason for that is because this table is a static table, and so I can't refer to uh, a member var or a non-static member variable from it. It has to be a static member. So we'll create this, and what should it do? Let's make this an void function to begin with. It will take an instance of the text assembler, and then it will take the instruction, and then what we will do is we'll do what we were doing in add. So we'll take these three, and instead of, yeah, this is a static method, we have to provide an instance. This is what that does. Good, so now we have 3 digits or 3 number values corresponding to the 3 register values of an R type instruction. And then we'll call asm dot, let's see, let's take a look at asm.asm.add. What does it do? It calls its own asmr, and asmr there does this work. So if we expose this, we'll make this an internal method. Then I can use that asmr instruction. Nice. And I will pass in my opcode, which is, let's call this opcode to be consistent. And then I'll pass that in. I'll pass in my destination, my source 1, and my source 2. And now, hey presto, I have an assembler that can handle R-type instructions for the Risc-V. All I need to do now is define this class. We'll create it we'll create a nested class here. And so what it will do is it will hang on to those values. So this first one is the mnemonic. The second one is the opcode. And the third one is an action, which given a text assembler and a opcode, performs the action. We'll call this a handler. And then all we need to do then is remember these values. So mnemonic will be remembered. This dot opcode will be remembered. And this dot handler will be remembered. Okay, good. Excellent. So there we have it. So now in our main code, what we'll do then is look in that table for something with that word as its mnemonic. So we'll go for each var v in, or let's call it encoder in encoders, or as an encoder, encoders we call it. For each one of those, oops, for each one of those records, what we'll do is we'll check to see if the encoder, if its mnemonic is equal to W, then we will invoke the handler and we'll pass in our this and the handler's or the encoder's opcode. Now, one thing that we want to do also is make sure that after we've expected the number, we also expect the end of line. So what we'll do here is we'll say expect end line. Good. That's a new void method. And so what we'll say is if get token is not equal to token dot end line. Of course, it's safe if we see an end of, okay, so let's do this. If we see the end of file here, it's also okay. So we'll get the token and we will, yeah, we will say token is get token. And if the token is equal to token dot end of file or token is token dot end line. If either of those is true, then we're happy. But if we're not, then we will say an end of line. And then we want to do is skip, call that method. Oh, that's a static method. What do we call it? Skip until token end of line. Ah, we're not returning anything from here. So that should handle one ASM instruction. So in our main code, we will spin through here, and if we find a handler, we'll let the handler deal with that one assembled line, and then we return true. If we can't find an encoder, though, we'll end outside of the loop and we'll fall through to this. So this allows us to handle regular cases inside of that table, but if we have some odd instructions that we need to deal with, then we'll handle them outside. So now we can remove the support for add because we've already implemented it. And we could add another record for sub, and we've already implemented that. No, we have not. Sorry, we have not implemented sub yet. So, but now it's easy because all we have to do is go over to the other assembler and find the instruction sub and basically steal this and then go back to our test assembler and look at add, and then we'll add sub here. And that one also uses ASM-R to encode. Nice. We haven't written a unit test for sub. Let's make sure we have one. Also, we're doing a lot of boilerplate here. It seems like we could uh, encapsulate all this into a single method called test. So I'm going to do that now, refactoring this on the fly because you definitely want that improvement. Let's do it on the add-I function. So rather than doing all this boilerplate, we would prefer to do something like this. We'll say run test, where our program will be add I 201 new line. Of course, this could be any string. And then as a second argument, we'll pass in a constructor that will allow us to build the assembly language program that we're expecting. So in this case, add I 201 would be the second option, or a second parameter. And let's format that a little nicer. Now this would be then some variable what we'll call the ASM source. Well, let's just call it ASM for now, or ASM source. Okay, source. And then this method would then get a builder, and we'll pass the assembler into the builder, and that would be that. So now our run test would take this the ASM source, and we would take a action that takes an assembler. We'll call it a builder. All right, let's run all of our tests. Actually, now that we have this, we can add a test for sub. And so sub, the subtraction instruction will look something like this. And let's add a deliberate error here just to prove to ourselves that our unit test is actually testing the code question. Let's run our alerts now. And sluggishness in the computer again. Yep, it's taking a lot longer now. Yep. Okay, it's definitely slowing down again. So interesting. Um, my machine gets slow after about 3/4 of work. Very strange behavior, but all right. We'll have to live with this. Let's just get our test to pass. Okay, sub is failing. But sub is failing because, well, we changed the encoding. So if we change it back to 2, or sorry, let's find the sub again. There. So if I change this back to 201, I expect this now to pass. Let's verify that. And indeed it passes. Fantastic. So we are in a good way. Uh, we're very, very close to now being able to just transfer all of the encodings that we previously had in this assembler class and just move them straight over here into this table. And the table will automatically handle all of these instructions for us. I'm going to add a final one for add I because why not? Before closing out today's session. And we'll put it right here. And again, it's a literal string for the mnemonic followed by the instruction encoding itself. But notice at this time we need to call a different method called asmi, like so. And now we need to implement asmi. And the way to do that is to base it off of the other asmr method that we already wrote. But in this case, we are going to call the asmi method, which is not exposed as internal yet. So now we have that. That looks good. And then we can remove the special case that we added for add I. And then we run all of our tests. And voila, it runs. So, as you can imagine, the process of converting the remaining instructions into this table is going to be very mechanical. I am not going to bore you with that, but next session, we're going to have to address what happens when we make a symbol reference. For instance, what happens if I write the following code? So I write a run test, and this is the jump and link instruction, the one that we use to call a subroutine. And I don't want to mention a raw address. I just want to be able to say Sterlen like this and have the resulting code called Sterlen. Now, this is a symbol reference, which involves generating relocations. And currently, our code doesn't, our new text assembler doesn't quite handle this. So, in our next session, we're going to be looking at how to implement jump and link and then go back to add I and make some improvements there. But that is enough for today, I think. So, thank you so much for watching. And as always, if you are interested in seeing specific features, just reach out on the channel. The code is uploaded to GitHub as well, so you can take a look at that at your leisure. Thanks again for watching, and have a great day.